Today we're going to start a new chapter where we learn about how to analyze trusses. Let me start by sketching out a picture of a generic truss. Like that, maybe it's pinned at one side and sitting on a roller at the other. And it might have some forces applied to it at different locations. I want to talk about what makes a truss and how this can impact how we analyze it. In a truss, all of these members, all these different pieces, these bars are all connected at very simple joints that we're going to treat like pins. So because of that, if you notice, each of these members is pinned on one end and the other end and has no other forces anywhere acting along it. So what we say is that a truss is going to be made up entirely of two force members. So that means that any supports we have, like this pin and roller, have to be applied at one of those pins, one of those joints, and any load we have has to be applied at the joint. We can't treat a truss as having any kind of distributed load. We can't treat it as having a couple moment. We can't have a fixed support. All we can have are pins and rollers, and loads applied at the joints. We're going to treat it like it's pinned together at all of those joints. As I said, we can only have forces applied at the joints. So remember what two force members look like. A two force member only has forces applied at two locations. And what we saw a couple of weeks ago is because of that, it can only have forces at those pins that act in exactly equal and opposite directions, and they have to be lined up with that dashed line that connects those two locations. We can't have a force right and left, or it would start spinning that direction. And we need these two guys to be exactly equal in magnitude and opposite in direction. The other picture we could end up with, same exact truss member, same 2 points, we could end up with the forces pointed in that direction. Both of those are possibilities. We call this situation on the left tension, because it means that the forces that are being applied to that member are tending to pull on it in tension. And we call this on the right compression. Now, we very rarely draw the free body diagrams of the individual members because, as we saw a couple of weeks ago, while we can figure out the direction of the force from this diagram, we can figure out that this force on the top and force on the bottom have to be exactly equal and opposite in direction, we can't figure out how big the force is from a free body diagram like this. So it's limited in how useful it is. Instead, what we're going to be doing is drawing free body diagrams of the individual pins and joints. And the thing I want you to remember is whenever you draw a free body diagram, here's a free body diagram. All the forces you draw on there are the forces that the things you aren't drawing, the pins, the joints, the roller supports, the other members, drawing, what is it that all of those other things do to the thing that you're drawing? So these are the forces that the pins apply to the members. That's really important. I'll show you why in just a second. Forces that the pins apply to the members. These are not the forces that the members apply to the pins. They're the forces that the pins that we're not drawing apply to the members that we are drawing. Okay, so here's our overall solution technique. We are going to start every one of these truss problems by drawing a whole free body diagram of the entire truss still assembled. Once we have that free body diagram drawn, we are going to write equilibrium equations. And we are going to third use those equilibrium equations to solve for all of the reaction forces, or as many of them as we can. Very important. These 3 steps you already know how to do. We've been doing this for the last couple of weeks in class. We still need to do those steps when we're doing truss problems. Today, we're going to talk about the method of joints, in which at this point, what we're going to do is draw a joint free body diagram. Well, a joint free body diagram is a particle equilibrium kind of problem, right? We're going to have just a dot with a bunch of forces acting on it. So once you have that, you'll remember from our chapter on particle equilibrium that since all the forces meet at a single point, we will only be able to sum forces. We won't be able to sum moments. So our 5th step is going to be writing those equilibrium equations for the joint. And 6 will be to solve for the force in the members. And then we're going to repeat steps 4 through 6 as needed. until we have solved for every member force that we need. So what you're going to notice is we're going to be drawing a diagram, writing equations, solving. Draw another diagram, write equations, solve. And possibly drawing more diagrams of joints and writing equilibrium equations and solving. So let's jump right into our first example. So we have this. It's the simplest truss I could find. It only has 3 members. They're pinned at A to the ground. At C, they're pinned to a roller or rocker, and at B, they're simply pinned together, and there's an applied external 500 Newton force. I told you the first step was going to be that whole free body diagram. To the right, we have a 500 Newton applied force. At C, we have a rocker, so you can either call this CY or the normal force at C, because all the ground can do there is prevent up and down motion. And then A is a pin, so we can have both an AX and an AY. And those are all the forces that act on the whole free body diagram. So next we can write out equilibrium equations to solve for those 3 unknowns. I would like to sum moments about point A first, because that's where most of the unknowns are. And in doing that, I get CY, which appears to be 2 meters away from point A. That's causing a counterclockwise moment. And then clockwise, I have minus 500 newtons times 2 meters. I have a 500 Newton force 2 meters away. That perpendicular distance is also 2 meters, and it's causing a clockwise moment, so I will call that negative in my equation. And solving, I get that CY is exactly 500 newtons. It comes out positive, which means it does in fact act upward like I guessed. And now that I know one of my unknowns, I can sum forces to solve for the rest. So if I sum forces in the X direction, I've got AX to the right and my applied 500 Newton force to the right. They have to sum to 0. So AX will come out to be minus 500 newtons. And negative means I drew it in the wrong direction on my free body diagram. So AX is actually going to be 500 newtons, not to the right, but actually to the left. And then finally, if I sum forces in the Y direction, I will have AY plus CY equals 0. Well, CY was a positive 500. So I get that AY is minus 500 newtons, or AY is 500 newtons. It acts downward. So now that we've done the first 3 steps, the whole free body diagram and equilibrium to find the reaction forces, now we can go and analyze joints. My tip here is, since analyzing a joint is like particle equilibrium, you can only write 2 equations. You can sum forces in the X and sum forces in the Y for each joint. So my suggestion is always start with a joint that only has 2 unknowns. In this case, you could start with any joint, because this joint has 2 members coming together. This joint only has 2 members coming together, and this joint only has 2 members. So it makes very little difference which joint you start with. I chose to start with joint A because I like joints where all the members are in the X and Y direction. I don't have to deal with sines and cosines of angles. So let's start with a free body diagram of joint A. Acting on it first are my reaction forces. AX acts to the left and AY acts downward. So AX is 500 newtons to the left and AY is 500 newtons downward. And I do find it helpful to draw these in the direction they act if I know what direction they act in, especially for my external forces. Now I've got those member forces that are internal to the system. Sometimes you can guess and you can figure out which direction they're going to have to act. Other times you can't. So my default is I draw them acting in tension, whether I know which way they're going to act or not. And there's a reason for that. If I always draw my unknown internal loads in tension, I always know positive will be tension. And if any of them come out negative, I know negative means compression. Tension on a joint diagram looks like that. This would be the force in member AC. Right? I want you to remember, if I drew member AC in tension, it would look like that. The force that the pin would be pulling on it, pin at A would be pulling to the left, pin at C would be pulling to the right. It's getting tugged on in tension. But that means a force to the left is what the pin does to the member. So when I want to draw what the member does to the pin, it has to be in exactly the opposite direction. This is Newton's third law at work here. So this means that the member is tugging to the right on the pin, or if the member is over here, the pin is tugging to the left on the member, equal and opposite forces. Tension in member AB would be straight up. Force in member AB, because the member is up above point A, and if the member is pulling up on the pin, we call that tension, because that would mean that the pin is pulling down on the member. And that's our whole free body diagram. So next we go and do equilibrium equations for it. So I want to sum forces in the X. And doing that, I've got FAC to the right minus 500 newtons to the left equals 0. And FAC comes out to be 500 newtons. Because it was positive, it means the member is in fact in tension. Next, if I sum forces in the Y direction, upward I've got FAB, and downward I've got 500 newtons. Those have to sum up to 0. So I get that FAB comes out to also be plus 500 newtons. It's also positive. I had drawn it assuming it was in tension, so it is in fact in tension. And we're almost done. We found 2 of them. There's only a third member to solve for. And we can either choose to draw a diagram of joint C or B. We do not need both of them, but if you would ever want to double check, you could go and double check by doing the other one. I did joint B in my notes. So at joint B, what do we have going on? We have somebody applying a 500 Newton force to the right. So draw that on there to the right. And then member AB is in tension. So because of that, right, AB is being pulled up and down by the pins. So if the pin is pulling up on member AB, that means the member is pulling down on the pin. So because it's in tension, I'm going to draw the force in member AB as pulling down on the pin. This does not mean that the pin is pushing down on the member. This force on this diagram is what the member does to the pin, not what the pin does to the member. And then finally, BC is at an angle, and I'm just going to guess it's in tension. As far as angles, that member is at a 45-degree angle, so this force is also at a 45-degree angle. Now, equilibrium, we can sum forces in either the X direction or the Y direction. They will both give us the answer. There's only one unknown to solve for here because we already know FAB is 500 newtons. Summing forces in the X direction, I've got 500 newtons to the right plus FBC times the cosine of 45 degrees equals 0. Solving, I get FBC comes out to be minus 707 newtons. And the negative sign means that FBC has a force magnitude of 707 newtons and it is in compression. It means I drew it the wrong direction in my diagram. So instead of the member pulling on the pin, the member is actually pushing back on the pin, and we solved the problem. Those 3, AC, AB, and BC, were our 3 unknown members. It turns out 2 of them are in tension and 1 of them is in compression. Let's go try a harder example. This one has a lot more members and we need a lot more diagrams to solve it. This one is pinned at A and pinned at B. That's kind of new. We've never had 2 pins together. We'll have to see what that means in a minute. And it's got 2 forces acting on it. And it looks like altogether I've got 1, 2, 3, 4, 5, 6 members to solve for. No matter how complicated the truss is, though, the first step is always a whole assembled free body diagram. We need to draw everything that acts on it. So A is a pin. At a pin, we will have AX and AY. I should say A is a pinned support, meaning that the ground is supporting it through a pin. That's a little bit different than these internal pins that we're talking about. We have pin supports where the ground is supporting through a pin. We also then have pins that are used simply to connect members to each other. So A is a pinned support. At a pinned support, you draw AX and AY. And we also have a pinned support at B. So let's draw a BX and BY and just guess a direction. Then up at the top, someone was pushing with 600 newtons to the right, and at point E, someone's pushing with 900 newtons to the right. Once we have a free body diagram, we can write equilibrium equations to go with it. When we do that, I like to sum moments first to see if I can get an equation with just one unknown in it. Before I do that, I might want to point out that I've got 4 unknowns. Do you remember 4 unknowns is usually bad for a two-dimensional problem because I can only write 3 independent equations. So I'm not actually going to be able to solve for all 4 of these just yet. Let's see how far we can get though. So if we sum moments about either point A or B, I did point A in my notes. Moments all have to sum to 0. The forces at A do not cause a moment at A because they go right through point A and they have 0 distance. And actually BX, can you see that BX is lined right up with point A also? No perpendicular distance away does not cause rotation. So I'm only going to have BY, a distance away, causing counterclockwise rotation. My 900 and 600 Newton forces will both cause clockwise moments. So counterclockwise, I've got BY and its perpendicular distance is 2 meters. And then clockwise, I've got 900 newtons. Its distance away is also 2 meters. And 600 newtons, its distance away appears to be 4 meters from point A. Again, we're doing perpendicular distances. So solving that, I end up getting that BY is equal to 2100 newtons, and it comes out as a positive, which means I correctly guessed upward. Now I can sum forces in the Y to solve for AY. I've got AY plus BY, which is 2100 newtons, equals 0. AY comes out to be minus 2100 newtons, means I drew it in the wrong direction, and AY is actually 2100 newtons, not up, but down. And then let's sum forces in the X direction. It's our other equation. See what it gets us. Summing forces in the X, I get AX plus BX plus 600 newtons plus 900 newtons equals 0. So it's a great equation, but I can't solve for it. And there are no more equations that we can write. We've already written 3 equilibrium equations. So we're going to have to go ahead with what we know. We know 2 of them, but not the other 2. We need to start picking joints to solve. And as I've mentioned before, you want to pick a joint that has very little going on. Joint E would be a very bad choice to start this problem because it's got 1, 2, 3, 4 members. We don't know the force in any of those members. C is a little better. There's 3 members there, but I can only write 2 equations. So I want to start with A only has 1 member, B has 2, and D has 2. I want to start with the easiest one. Let's start with joint A. Make our life as easy as possible. Here's joint A. Acting on it are AY, which is 2100 newtons downward, and AX, which we're guessing X to the right, but I have no idea how big it is. And then finally, I'm going to have a tensile or compressive force from this member either pulling up on the joint or pushing down on the joint. I'm going to guess tension and draw that as the force in member AE pulling up on the joint. Okay, we can go solve. If I sum forces in the X, I get that AX is 0 because it's the only force in the X direction on that pin. Now we can go back to this other equation. Combining these 2 together, I'll get that BX is minus 1500 newtons, which means BX is 1500 newtons to the left. So I mentioned last time, if you have more than 3 unknowns in a 2D problem, you can solve for the other unknowns, but you need more equations. You need a more complicated analysis. And here's an example of one where we did have 4 unknowns, 2 at B and 2 at A. We're able to solve for them, though, now that we know a little bit about trusses and 2 force members. Okay, returning to our purple joint A diagram, I can also sum forces in the Y direction. Call upward positive. We get FAE minus 2100 newtons equals 0. So FAE is 2100 newtons. And because it was positive and I drew it as acting out and away from that joint, that is tension. Means that the member is pulling up on the joint or the pin or the joint is pulling down on the member. That's all we can get from joint A, but we now know one of our 6 unknown member forces, 2100. So now we got to move on to another place to make some more progress. I actually did joint D next. Seemed like a good option because it's only got 2 unknown member forces. I do find it really helpful to switch colors with each joint because it helps reinforce in your mind that these equations go with this diagram. So joint D, there is a dot for joint D. Someone is pushing to the right on it with 600 newtons of force. It's got a straight down member, member DE. I'm guessing tension. I might be right, I might not. And then there's this member DC off in some direction that I'm going to need to figure out what the direction is. So going up and looking at the picture, D to C is along this line, and it's 4 meters high and 2 meters wide. So if I wanted to draw that as a little triangle, it's a 4, 2, squaring those, adding them and square rooting, I get square root of 20 on the hypotenuse. Again, for those two unknowns, I just guessed that they were in tension. I think that probably one of them is not in tension. I want to sum forces in the x direction first on this one. And the reason for that is that this unknown is in the y direction. So if I sum forces in the x direction, I will only have one unknown. So to the right, I've got 600 newtons plus a component of FDC. It's going to be FDC times the horizontal side of that triangle, which is 2, divided by the hypotenuse, which is square root of 20. That has to equal 0. Rearranging, we get that FDC comes out to be minus 1342 newtons. So if we're rounding that to 3 sig figs and calling it our final answer, I would say that FDC is 1340 newtons in compression. The negative means I guessed the wrong direction. That member is not pulling on the pin. The member is pushing on the pin, and the pin is pushing on the member. So pushing in is compression. So now let's do the y direction. Summation of force in the y is 0. Up is positive. So I've got minus FDE minus a component of FDC, and it'll be the 4 over square root of 20 side, equals 0. Let's bring the FDE to the other side. So I've got minus FDC, which is minus 1342 times 4 over square root of 20 equals FDE. Those minuses cancel, and I get that FDE is a positive. It comes out to be 1200 newtons, and because it's positive, it is in tension. So what that means is my 600 Newton load to the right means that FDC actually has to go upwards so that it contributes a leftward force in the x direction to counteract the 600. And then that means FDC will have an upward y component to counteract the downward y component from FDE. So we're making good progress. We've got 3 of them solved now. The next joint that I thought made sense to work on, because now I know FDC, I think if I move down to joint C, I'll be able to find these other 2. So let's do joint C. Joint C looks like this. We have a member force to the left. That's the force in member CE or EC. We have the force in member DC that we just found. Now you have a choice at this point if you want to draw it on the diagram in compression, now that you know it's in compression, or if you want to draw it in tension and remember that it has a negative magnitude. I don't like keeping negative magnitudes very much, especially since I haven't even drawn this diagram yet. So why don't we draw it in compression as we know it actually acts? So this is the force in DC, and it is 1342 newtons in compression. Just to remind myself, I know the magnitude and I know it's in compression. It's pointed that way. But now the other member down here is lined right up with it, but I don't know if it's tension or compression yet. We'll just draw it guessing in tension. This will be the force in member BC or CB. You can order those any way you want. Now I need to go and sum forces. I can sum forces in the X or the Y direction. I want to sum them in the Y direction first because this force has no component in the Y direction. So if I sum forces in the Y direction, it equals 0. I have pointed downward a component of the 1342 newtons. And the vertical side of that is the 4 over square root of 20. And then also downward is FBC times 4 over square root of 20 equals 0. Solving, I get that FBC is minus 1342 newtons. So my final answer I would report would be round to 3 sig figs, 1340 newtons. And because it came out negative, it is also in compression. I think that ought to make sense, sort of, that if we're pushing down, this member up above is pushing down, this one should be pushing right back up at it, and those should cancel out. If we sum forces in the X direction, look what happens. I've got a component of FDC acting to the right. So that's 1342 times 2 over square root of 20, acting to the right. Then I've got FBC, which is also acting to the right. So I'd call that plus FBC, but for this diagram, I found FBC was actually a minus 1342 times 2 over root 20, right? It's drawn to the right, but because of the negative, it actually acts that way with a leftward component. And then finally, minus the force in CE equals 0. And do you notice those two terms cancel? Cancel, cancel, and we get that the force in CE is 0. It's neither tension nor compression. This guy is called a zero force member. And we're going to see zero force members a few times in the trusses that we analyze. They very commonly happen when you have two members that are in a perfectly straight line with each other, and then a third member that comes in at some different angle. It could be perpendicular or that way or that way. Any angle, this extra third guy coming in, these two are always going to end up needing to be equal and opposite to each other, and the other one is 0, unless you also have an external force applied right there. So you're looking for cases where you don't have an external force and you have two things in a line with one more meeting. What'll happen every time you have that is the forces in those two members that meet will be exactly the same, and the force in this third guy, the odd guy out, is going to be equal to 0. We need to solve for one more force in one more member. We need this in member BE, one we haven't dealt with yet. And we can either analyze joint B or joint E. I'm going to pick joint B because it is simpler. Joint E has got a lot of members, even though EC we now know is 0. I think joint B is simpler, so let's do that one. Joint B looks like what? It's got a pin support there. Remember, B was pinned supported by the ground. So at B, I need to include those reaction forces, the 2100 newtons upward and the 1500 newtons to the left. So we draw on here BY, which is 2100 newtons upward. And we also need to draw on here BX, which is 1500 newtons left. And now what happens at B? We've got these two members both at angles. We've got BC, which we actually figured out was in compression. So it's pushing down on joint B. And then we've got force at member BE that could be tension or compression. I don't know. So we've got the force in BC, which we know is 1342 newtons in compression. And then we have the force in BE that is unknown. Let's solve for it. We can either sum forces in the X or sum forces in the Y. If we do the X direction, we get minus 1500 newtons from BX plus a component of the 1342 from that compressive force from BC. And I need the X component, which will be 2 over square root of 20. And then finally, I need minus FBE, and I need to figure out what angle that is. Going all the way back up to the picture, it goes left 2 and up 2. Oh, that's a 45-degree angle. So if this is a 45-degree angle, I just need to use cosine of 45 equals 0. So solving, FBE comes out to be negative. I guessed wrong once again on my direction. Minus 1270 newtons. So FBE is 1270 newtons in compression. We solved the whole problem. We did not need the free body diagram of joint E. We didn't need to sum forces in the Y direction at this joint. If you ever did sum forces in the Y direction, it should come out to be equal to 0. We can double check that. Summation of force in the Y equals 0. This is just a double check. I've got 2100 newtons upward from BY, and I've got minus 1342 newtons. I need the vertical component, which will be 4 over the square root of 20. And then FBE, I drew it as acting up and to the left, but it's actually going to act down and to the right. So either way you do it, you're going to end up, it's going to be pushing downward, minus 1270 sine of 45 degrees. And if I toss all of that into my calculator, I get 0. Little rounding error, but basically 0. And you could do the same thing if you wanted to analyze joint E to double check that everything works out. The thing to keep in mind, a few things. Always start with a whole free body diagram. Then use your equilibrium equations to solve for as many of the unknown reaction forces as you can. Usually you can solve for all of them. Next, pick a simple joint, include any externally applied forces or reaction forces on there, whether you know them or not. I like to draw all of my unknown internal forces in tension so that if it comes out positive, it's tension. If it comes out negative, it's compression. And then you work your way from joint to joint to joint, all the way around the truss until you solve for all of your unknowns. So we then went to joint D and found these two. Then we went to joint C and found these two. And then finally we went to joint B to finish the problem. And that's how we do the method of joints to analyze trusses.